I promise that I'm going to give you an example of a generative domain adaptation technique. This is an example of them, but let's review or remember what was the task, domain adaptation. You're going to see this scenario a lot when you're doing robotics, when you're doing self-driving cars, that you can actually have simulation engines. They could be game engines, they could be renderers. These are going to give you images. They are simulated images. They are not coming from the real world. And the cool thing is that in the simulated environment, you know your ground truth. And you can generate as many data as you want. It is unlike taking a car and driving it on the real streets. That one is constrained by the laws of the physics. There is only so many images that you can collect. But in the synthetic world, you can keep generating images, parallelize stuff, and generate as many images as you like. Not only that, you can also label them automatically. You know your objects. You can do semantic segmentation easily. You can put bounding boxes easily. Okay. This is the source domain. In the target domain, it's going to end up being real data. There's going to be a discrepancy in the distribution of real and synthesized data. Therefore, you need to do domain adaptation. What are the methods that we saw or exist? You can look at the representations between these two domains and then try to correct them. You put a mapping from the target representations to the source representations, and you try to correct them using that mapping. This one we didn't cover. The other alternative is you're trying to learn or extract features that are domain invariant. They don't give away information about is this a source image, is this a target image. This one we covered 3 papers on that. The other one, which this paper also belongs to that class, is you're gonna do some transformations in the pixel space. And for this, think of image-to-image translation. And we were doing that when we were doing conditional cats. We had an input image, and then we were translating it into a target image. Let's see why that is useful. The method is pixel DA. It's domain adaptation at the pixel level. This is going to be unsupervised. And this one is less flexible compared to trying to extract features that are domain invariant. This one has its use cases whenever this assumption holds, that the difference between the source domain and the target domain are because of low-level differences rather than high-level. What do I mean? They could be that one domain data is more noisy than the other domain. Maybe one domain has a lower resolution compared to the other domain. They have different illumination. Maybe some of the images in one domain are black and white, the other domain are color. This is not at the high level where the objects could have different forms. For instance, you look at a dog from a close perspective rather than take the picture from far away. And it's not based on geometric variations. Okay, let's remember the data in the source domain is labeled. You have an S of them. I is counting your data. Your target is unlabeled. These are just images. Now you're going to do translation. You're going to translate. You take a source image, push it through a generator. That's going to give you a fake image, or you can call it adapted. Take a source image, push it through a generator, translate it into a fake image. We have this Z vector, which we also had whenever we were doing generative processes or GANs, and it has its own parameters. And the noise you can keep sampling from a noise distribution, perhaps normal distribution. Now, why is this useful when it comes to domain adaptation? It is useful because you can take a source image, push it through your generator. It's going to give you a fake image that is going to look like your target images. Okay, you just translate it from source to target at the pixel level, but something good happened. You know the corresponding label for that image. This image is just warped, translated, but you know the corresponding label. And this could be your new data set that you can train your classifier on. And this is exactly this sentence. You can train a task-specific classifier as if your training and test data are coming from the same distribution. You can think of XS as your training. You can think of XT as your test data. And there is a distribution shift between source and target, or training and test. How do you do your learning? What are your objective functions? You're going to write a discriminator. Why do you need this discriminator? You need a discriminator because you need to train G, so that G is going to generate images which are XF type of images that are hard to be distinguished from the target images. Exactly, you're trying to distinguish between fake and real images. And then you're going to write down your classifier on top of that, on top of this data set. Okay. How do you train that? What is your loss function? You're going to have LD and LT for the task, for the classification task. LD is your domain loss, and its job is to train your generator. You take a source image, translate it into a target image. These are going to give you some fake images, and they should be indistinguishable from the target images. So fake images, these are real images in the target domain. And then you're going to have your discriminator, training G. And your task is exactly this observation here, that some of your data are actually source data, and you know the corresponding label for them. You can have a classifier on top of it. This is supervised learning. Maximum likelihood or minimize the negative of the log of your likelihood, or cross-entropy. The other one is you take a source image, you push it through your generator. These images are going to look like the target images, but the cool thing is you know the corresponding label. And then you're going to write down your objective function and sometimes maximize your discriminator and minimize the objective functions of your generator and your classifier. And these are one-hot encoding vectors. Okay. Any questions so far? Was everything clear? So you can think of this slide as a very important application of GANs. We saw a lot of applications. Here's another one. You also have some prior knowledge that you can actually incorporate in your objective function. This one is a minor detail, so don't worry too much about this. And let's say your prior knowledge is that the objects that are being rendered, they usually have a black background. This is how you were doing your rendering. These are simulated data. These are synthetic data. And then you're going to change the background. You're going to put those objects on different backgrounds, colorful backgrounds. That's your data. These are your synthetic data. What is the prior knowledge that we have is these rendered images, they're going to have similar foregrounds and different backgrounds by construction. This is how we constructed our simulated data. And we can actually leverage that knowledge that you have about the way that you generated your synthetic data. How can you leverage it? You're going to put it in your loss function. You're going to add an extra term in your loss function. What is that term? You say that if I take a source image, which is rendered, generate an image in the target domain, compare it to the source domain, to the source image, only look at the foreground. So N is a mask. Ignore the background, only look at the foreground. This circle is just a Hadamard product. It's pointwise production between two tensors. So what you're saying, take a source image, push it through your generator, and compare the fake image and the source image only when it comes to the foreground. Ignore the background. And don't worry about this extra term for now. That is the mean squared error that you're going to put here. This is a constraint. This is some physics, some prior knowledge that you know about the generative process, about the way that you synthesize your data. But this is a modification of mean squared error. You have some modifications here. And this pairwise mean squared error is not sensitive to the absolute value of the pixels or the intensity of the pixels. It is sensitive to the relative value. And this makes sense. You don't want to compare everything pixel to pixel. You want to compare how things are changing relative to each other. You are subtracting the generation from the source, and then you're basically multiplying by m. This is the dot product now, and then you square. So there is a summation going on inside the square, unlike your mean squared error, which is pointwise square. So there is a summation here inside the square there. Okay, but this is just a minor detail. This is your binary mask separating foreground from background. And then you can look at the generated images. One way to see whether you actually adapted your domains is to look at the generated images. You take MList images or MList type images as input, and then you can take them, push them through your generator, and these are the type of images that you're going to see. And as you can see, they have different background. The foreground is the same, they have different background. And to make sure that you are not just memorizing the data, that this generative process is actually able to generate a variety of images outside of your target, you can look at the nearest neighbor of those images in your data set, and you can see there is some differences. For instance, this 3 is different. The nearest neighbor is actually a 1. The 9 here, the nearest neighbor is a 1. This is just to test that you didn't memorize your data. And then you can compare the method when you're doing transfer learning or domain adaptation. We covered DAN, and this is pixel DA. And this is the oracle. This is the best that you can do if you train on targets. And it's closing the gap. Any questions about pixel DA? Was everything clear? Okay, perfect.